All right. Well, great. Thank you so much for having me today. I was somewhat surprised when the organizers asked me to present, because what we do is not nearly as exciting as some of the other keynotes we've heard from, like connecting electronics to brains and things like that. So it's a little bit more pedestrian, but I hope you'll enjoy the story. And it's going to end up being a interesting conversation. I'm not going to get into as many technical details so much as talk about the journey, because as we were talking through this, there was a desire for us to talk about the open source LTE core that we had worked on, initiated, and partnered with Intel on. And that ended up leading into some other interesting work related to natural language processing. And I think the journey itself is as important as the endpoint as it is in many R&D situations. So I'm going to focus on trying to outline what we were trying to accomplish and how we got to where we're at today. The word cloud is, it'll come up at the end as well. It's what the team put together about everything related to the project itself, and you'll see it embedded in there so much testing. That was a big theme in all of this. As Karthik mentioned, for those who are not in the US or don't follow the US mobile market, Sprint was acquired by T-Mobile April 1st of this year. This work talks about Sprint in some slides because that's who we were at the time. We're all T-Mobile now, and this is where we're doing our work going forward. So first, talk about who's involved in this. My team, the Advanced Technologies Innovation Team, is responsible for forward-looking. Our CEO talks about looking around corners for new technologies. I'm not sure we can quite do that, but whereas most of the company is focused on delivering results in the next quarter to year time frame, we're sort of looking forward, helping to prime the pump so that the engineering teams that are our internal customers have initial views and analysis on technologies that may impact them in the future. And that's really how we got into this particular endeavor. As we'll talk about later on, we also partnered with Intel Labs and GS Labs on the open source core itself. And then it is actually now a project as part of the larger program within ONF, and so open sourced and available for everyone to look at. And there'll be a link later on in the presentation. So we're going to go back to 2013 and talk about what were we trying to solve at the time from an R&D perspective. It's somewhat funny to think about it now, given that the industry as a whole is embraced virtualization wholeheartedly, and it's widely accepted. But back in 2013, it was very early days. You had the early white paper on NFV, and really as an organization, we were trying to get our arms around how possible is this. Obviously, you can pass bits, but there's a lot that happens in our vendors' proprietary gear that we don't get exposed to because it's a black box, and we really need to understand better how we're going to move bits in this sort of general purpose computing environment. If we get it to work, if we got it to work, it was going to have a lot of promise to lower costs and increase flexibility, and it has. But at the time, realistically, what we were trying to figure out was how fast can we run at this? We knew it was going to happen eventually, but was this something that was going to take a long time to develop, or something that would happen rather quickly? And now that we're in a stage where the industry is now really moving towards virtualized RAN and not just the core, and that's even has more real-time constraints associated with it, it's much the same problem where we're at today with Open RAN and trying to sort out exactly how fast we can go with it and what it can really accomplish. At the time in 2013, we really wanted to take realistic traffic models from our network, nothing hypothetical, real users, obviously scrubbed for privacy reasons, and really answer the question, could a single CPU core, or even just a single CPU, move 10 gigabits of traffic in a gateway? As we'll find out, that ends up being a laughable question, but at the time, we just wanted to make sure we understood what was really possible, and really make sure we did it like with any benchmark. It's very easy to get numbers you'd like by doing an easy problem. And so simply forwarding packets back and forth is not that challenging for a CPU. And really what we wanted to do was layer in all the functionality we have in our, at the time, proprietary gateways to make sure that we were looking at what the capability of NFV was from a really practical perspective with all the various functions that are in the user plane path for processing the bulk of the packets. So to answer that question, and really, how do we scale with the CPU and with cores as we add them for realistic traffic demands? We ended up turning to a great partnership with Intel. We still continue it to this day, although it's evolved and taken on new topics. But if I can't speak for them, but I think they would agree that it's been a great partnership, and we each brought a lot to the table. And I think that's really the reason why we learned so much from each other and why it's been such a fruitful relationship. They obviously brought a great understanding of their CPUs, how to optimize for them, for systems based on their CPUs. And we brought a lot of very practical understanding of the standards. I do remember that early on, some of the Intel folks were like, the 3GPP standards are this thick. How are we going to know exactly what we're supposed to do? Is it all equally important? And no, it's not. And so part of what we provided was a bit of practicality on that, and also the actual traffic dump from the network to use for testing purposes to make sure that that model was consistent, and what we were testing with was consistent with actual use in the network today. There was some early work published in 2015 with GPTK that really showed that you can scale to millions of packets per second, although there were bottlenecks. There's a link there to the document. That was based upon our traffic model and their development and some testing with early code they'd written and or commercial vendors and startups code. But it wasn't, it was basically just forwarding packets, and it wasn't the complete laundry list of functions that a packet needs to go on in its journey through a mobile core. And, for an example we include is, legally we're required to do child protection filtering. It's not a huge jump to do that, but there ended up being, in the end, we started with about 7 of these we included, and then it ended up being more like 17 or 20 individual capabilities that we added to this, and to make sure that as we loaded it up, we didn't break the scalability, or we knew how things operated in that environment. So we really, in 2016, after we'd gone through this early work, I decided that we really needed to set our eyes on a different goal, which was developing something ourselves, building it ourselves so we could learn about the intricacies of implementing the standard and make it as functionally similar in both capability and actual configuration and use as the proprietary network elements we had in our network at the time. And the goal, again, was to forward a minimum of 10 gigabits per second per CPU. And that was an R&D effort, endeavor to really understand things. At the time, we had no clear path to how we would use it beyond that. As we evolved in this, we'll get into it a little bit later, we did have a couple areas where we thought we would end up putting this in the network for lots of reasons, including the merger and how that changes decision-making in a corporation. We never have put it forward at any of this in production itself, but the process aligning to that original question remained the same. Is really learning more about NFV. How can we really prep and help the experts in our engineering group that are deploying stuff every day really hit the ground running on NFV? And as we'll see, the questions evolved over time as well. So really what we did initially, and this was all proprietary at the time, is, on the left you have the typical LTE core. Some of those blue boxes would be individual network elements, and in some cases they might be packaged jointly in a network element. But largely these were packaged in proprietary boxes that a company would design the hardware, design the software, package it all together, certified it worked at a certain performance, and that made life simpler from some perspectives, but more costly. So what we really decided to do was focus in on, creating this scalable architecture. It was really heads down work for the first few months. I mean, over 300 designs. That's obviously many per day. So the teams were working very closely together between both companies, and really trying to get to the ultimate, not just for pure performance sake, but also scaling as we added more and more capability and function to it. A clear goal was to separate the control and user planes. That was already a trend in the industry, and with CUPS and LTE, and of course with 5G coming along, included in part of that as well. But in addition to that, we agreed to incorporate SDN into it, trying to make this core architecture more programmable and flexible as a result. And and within about 6 months, I think at most, we maybe 7, depending on holidays and so forth. Actually, after all that design work, it ended up working better than we ever expected. A little bit of debugging and after compilation, but beyond that, we were able to easily achieve 10 gigabits per second on a single CPU core, not just a CPU, but a single CPU core. And that work was then later presented at the Intel Developer Forum in 2016. In retrospect, we aimed too low, but we weren't sure what was going to happen. But we were also at the point where, and I'm speaking, I should have mentioned this early on. There were two authors in the first page. Lyle Burtz isn't able to be here, and he really should be. He's really the brainchild behind a lot of this. And he, I think, is somebody that I will put the email addresses at the end of the deck. I think if people are interested in talking further about this work, I think it's definitely somebody you should be involved with. But I think, part of the reason we wanted to do what we did, we didn't know what the art of the possible was, and we also figured we were going to be agile and adjust the R&D project as we went. And so, what we next decided to do was, okay, we have this interesting thing. We as two companies have learned from it, but there's only so much we can do with this code going forward. We can try to improve it. We'll probably do something to improve it somewhat, and we did. But around the same time, we were starting to look at options for and reasons for using a core this code specifically in the production network. A couple of opportunities were discussed. IoT, and to the degree you think of IoT as billions of really cheap endpoints and not hundreds or thousands of robots and cars in a sector. Then you really wanted to have the least cost core, and that was really a driving factor to see if this was a path forward. Kind of looking at sort of a Red Hat open source model where in working with other vendors that could be providing technical support and ongoing maintenance on the code, just so that we ourselves weren't the only ones with about 3 developers engaged doing all of this. And so that we ended up pulling in GS Labs for that as well. And there's some of these goals you see here were really obviously probably part and parcel of most open source projects. Get other people to use it, get them to start adding to it and doing more than we can do on our own. But there was another aspect of this which we'll see as we move forward. We wanted to use this as a demonstration platform for our own vendors on what we knew the art of the possible was. There were areas where there were features in the standard that weren't really implemented, had been promised, but never really delivered. And we showed that this was definitely possible. And as this project grew, it grew to include our competitors. So there was maybe part and parcel in some industries to work with your competitors in open source, part and parcel in academia. It was a culture shift for us to try to convince our management that this made sense and it was something that we should be pushing forward. The use of the outsource contractors was intentional. They've now built businesses where they have gone out and are supporting this same code base in production and other people's networks. And so it starts to take on a life of its own. You don't have any single operator or any operator feeling like they have to maintain the code base going forward, but can work with software development experts to continue to provide the maintenance and support. And we also wanted to, in this project, take this as far as we could to being fully production ready. As I said, we had several targets for that. And so compared to some open source projects, we really wanted to put a level of scrutiny around the testing and the feature set to make it fully functional and worthy for our own internal customers' use. And so we were actually under a great deal of scrutiny by them to make sure that we didn't deliver something that was fluffy and had some interesting capabilities, but wasn't near what they were getting from their vendors. So then in May of 2017, and there's a blog entry down at the bottom if you want to have look at more details on how this was configured and what performance we achieved. We announced C3PO, and yes, that is an acronym, so we couldn't get any geekier than that unless we made it a recursive acronym. And we put it out there and publicized it and tried to get some energy around it so that we would get more engagement and involvement. We did end up in the US having both Verizon and AT&T engaged, AT&T in the end more than Verizon. And Deutsche Telekom internationally, as well as some other operators, have embraced it and have been working on it and its later incarnations. And quite frankly, I've used it in production in at least some of their markets. A key aspect of this, you see the architecture on the right. We have the Open Daylight SDN controller that we provided and the control and user plane that Intel developed. A key aspect of this at the time was a lot of the literature on NFV talked about service function chaining and being able to add capabilities in the path of a packet by doing that. But it was very clear that had a lot of overhead and context switching between each of these capabilities. So part of what we wanted to do in sort of like a fast path, if you look at routers, a fast path approach, is for that 80-20, 90-10 rule of what most packets have to go through on the network and what can we do to optimize the performance of that. We ended up implementing initially 7 of these network functions in one rather than service chaining them together, and therefore not requiring all that context switching. Eventually, we scaled this to over 17 and had plans to go into the 20s. And some of that was more just to see where it would go than anything else. This first 7 was a first attempt to really mimic the bare minimum what would be needed in production for every packet to go through and be supported. So you have an SGW, PGW, DPI, the child protection filtering I mentioned, NAT firewall, and then the classification portion of necessary for service function chaining for additional capabilities we might want to add via that and obviously with a performance hit. We on the control plane side used at the time IETF FPC and connected the control plane with the SDN controller that way, also with OpenFlow. So now we had an ability to govern that via that API and SDN. And after we announced it in May, we finally released it in open source with the ONF in December of 2017. And like any of these open source projects, along the way we had some setbacks. So the day prior to our announcement, the CTF function that we were getting from the Clearwater project was deprecated and was no longer going to be supported. And so in some ways we were already out of date on the day we announced. But obviously we have to keep rolling with those punches and implement new capabilities. So in parallel with all this, I'll give you a sense of where this was going. We were taking NFV to production, but not where we initially thought we might. So while we had focused on gateways and packet forwarding performance, and along the way, senior management had decided, for lots of reasons, Sprint was rather late to implementing VoLTE. It was because we had a really efficient implementation, one of the only in the world, of 1x RTT Advanced of CDMA. And we'd invested in that a few years earlier. It was actually more spectrally efficient than doing VoLTE. And quite frankly, the whole industry was going through a lot of challenges making VoLTE work. And so we chose to sit back and let them take a lot of that early pain, get to the point where our vendors had learned from that experience and could help us implement VoLTE ourselves more rapidly and without as much impact to our customers. But as part of all this, senior management had decided, look, the NFV is important. We don't think we're going to be making any gateway changes anytime soon. We want to pivot and now look at NFV in production for VoLTE. End to end, every single part of the VoLTE and the IMS and the VoLTE call flow was virtualized. As far as we know, at the time, it was the first operator when we launched to have it completely virtualized in all aspects of it. But we were working with the core team to demonstrate the NFV functionality and some of the underlying, I'd say, the plumbing and the capabilities needed for NFV. To do all this on servers, we need a lot of tools, and be able to take, I didn't put the timing in there, but on the first bullet, be able to take a bare metal server with just Linux installed, get OpenStack running, and then install a VNF and make a first Vultr call all within 10 minutes. We demonstrated that in July 2017. So this work, we haven't talked about the tools, but there was obviously a lot of tooling that went into the gateway work we've been working on with C3PO, and pivoted and applied that towards the production network and helping the engineering team that way. So C3PO itself changed over this point in time. We demonstrated what we wanted to on NFV. We'd gotten enough learnings and skill set enhancements that we could be helping our production group, even though they had changed their targets. And now we really wanted to focus on net new capabilities that really weren't in the industry at the time. We developed an LTE API gateway into the core, which really had been promised. It was in the standards, but had been promised by vendors, but really had not been delivered. As you'll see in the next slide, we migrated from IETF FPC to the 3GPP PFCP because that was maturing at the same time. And another thing we did with Intel was look at the charging, the billing and charging elements, and say, hey, there's a lot of really sensitive stuff here, and it's important for us to maintain its integrity. It's important for us to make sure that this data is not somehow compromised if there were any incursion into the network. So we really want to add as much security to this as possible. And working with them, they agreed to implement the billing interfaces with SGX, their CPU extensions for hardware root of trust and the software guard extensions. And so we implemented that as a secure user plane as part of this as well. Really taking the project from an early demonstrator of what's possible with NFV to now an early demonstrator of features and functions that otherwise weren't really available from vendors in LTE, and really doing net new work. About the same time, we undertook an re-architecture of what we were doing. And I think what was important and interesting in this is, I didn't mention it, but Lyle Burtz was the actual author, editor of the IETF FPC standard. And to his credit, he saw it was there before the 3GPP equivalent, but to his credit, he realized that the writing was on the wall, that the bulk of the industry was going to be adopting 3GPP, and so we chose to take out his code and his baby, so to speak, and swap over to PFCP. And yeah, we also took out the SDN controller, which was really initially our entire contribution as Sprint at the time. The maintenance task and the overhead on it was high. But more importantly, from an open source perspective, we were getting no contributions from the community. So it wasn't really resonating that this was an important feature to have in the project. And if we were the only ones interested in that, and nobody else was, and others weren't contributing, it didn't make sense to continue forward at that point in time. I think the key learnings here were really getting this even more production ready. We had continued to evolve it. Our last release, fully implementing everything we intend to with LTE, will be at the end of this year. But in the process here, and this is where we start pivoting directions, we discovered a lot of issues in the specifications, which hampered our ability to move forward on PFCP initially, and then later on with other aspects. OMEC, so we also, at this point in time, C3PO was a standalone project within ONF, and it sort of got elevated to be a key part of MCORD, which is the mobile, M is mobile, and then CORD is central office re-architected as a data center, that MCORD program within ONF. And this is really where we started getting more and more momentum in the industry with our competitors. AT&T signed on and as co-leading this and working on it. Deutsche Telekom was doing the same. Deutsche Telekom deployed in production in a few countries in Europe, and as far as I know, still has it working there. Again, the goal, especially now as part of MCORD, was really to get it production grade or as close as possible. A lot of the functionality and more importantly, rigorously testing that functionality so that it was really ready to go for equivalent to what a vendor might deliver to an operator for its own internal operations testing. Really get the quality level to there to be the same. 9 releases. We're nearing the final release that's LTE related, at least. And you can see the GitHub link for those who are interested in looking at it, downloading it. It's obviously freely open for people to use and contribute to, or use for their own research or other uses. So this is where, at this point in time, as part of this process, there came a real key inflection point and change in how we were doing things. And this is really more from the software development side. We noticed an interesting trend. Like any software project, things started getting off track at some point. And so Lyle started doing what management does. Okay, this looks like this developer who's relatively new, less than 2 years experience. Let's swap them to do a different task and bring in a developer that's much more experienced. Get them to get everything back on track in terms of schedule, so we can keep moving the ball forward. What we found, however, was that no matter what the skill set of the developer was, the rate of progress was the same, and that began to concern us. We weren't sure what was happening, and started digging into that with nightly code reviews and really trying to figure out from all perspectives what was causing this. And to be honest with you, what happened here is we were limited not by the skill set of the developers, but really by the quality of the source documents for the specifications. And that's not meant to be a dig on the standards bodies. They have a lot that they need to accomplish, and the whole entire large industries are very much based on their ability to rapidly turn out standards. But over the years, they really had gotten to the point where there was a lack of clarity in some areas. And really, it was the standards documents themselves that were slowing us down in implementation. Now, I'll fully admit that if we were an existing network OEM that had been doing development of 3GPP for years and years and years, I'm sure there would be a developer for any particular part of the standard who would say, oh yeah, we always interpret it that way. And they would be able to do something quicker because they already had an internalized understanding of what they thought the standard was. But that also means that the standards tend to ossify things into relatively few players, and it becomes an issue where it's very challenging to get interoperability. It's challenging for the existing players to move their code base forward as new features are added, and it slows down the industry in general. I think that my general analogy for those who haven't been involved in standards development, you end up, just use 100 companies. There's far more than that in 3GPP. But if you have 100 companies going from around the world, some from 40, 50, 60 countries around the world, all going to write a standard, in the end, they all submit Word documents. They all take Word documents back, and there's probably 100 different interpretations of those Word documents. And so part of what we wanted to do when we got to this point was start to make source code a key demonstrator from a standards perspective. There's a lot of intellectual property concerns, rightly so. And so you're never going to get people submitting their production code to a standards organization. But whether it's pseudocode or it's just a simple mock-up in a language that no one would ever use in reality, Visual Basic or something, then at least it is a bit more specific and more precise in how it labels things than the human language. And that's really how we ended up migrating over into taking this work in parallel into NLP. So, the 4G and now 5G cores are based upon many specifications from many bodies. Ultimately, it's 3GPP, but those documents point to many other groups, notably IETF and IEEE. And not all of them, but some parts of those documents are as many as 30 years old. And in some ways, we don't need to reinvent the wheel all the time. If it's working and we don't need to change it, great. But the documents themselves are pretty old, and there's been multiple versions of them written by multiple authors that each come from a different perspective in their language capability. I native speakers in English may be helpful, but frankly, some native speakers in English don't do a great job of writing documents either. And so that was part of the struggle we were seeing, is how these documents had evolved over multiple decades, hundreds of thousands of pages, and really the ability for that lack of clarity was really something that was holding us back. So Lyle, the one person mentioned here, was actually Lyle himself. He literally hid in his basement for 5 weeks and developed a tool to dive into all this, FD tool. As he would say, he learned too much about linguistics, and we found over 3,000 issues in about 30 documents related primarily to the diameter spec you see on the right. So this tool would take in the RFCs and 3GPP specs and others and output an intermediate format for a tool called diafuzzer, which is for testing of diameter. That then allowed us to parse the English language versions in the specs into a common format, and then look at how consistent or inconsistent they were. I asked for a simple example. It's hard to show how inconsistent some of these things are. Sometimes it's simply, and it could be across documents. It could be one 3GPP document calls something, whatever it might be, as a long variable name or a long parameter name, and there's just an earlier version in another document that never got scrubbed. Now, people can make that connection, especially if they've been in the standards a long time, but it also holds back the ability, as that cruft continues to increase, and some of these changes in specs especially cross documents, where one author may be perfectly consistent within their one document they're writing or editing, but the other documents may not be updated over time or not completely updated. So you get tables like this that have different formats and different elements, and it ends up being quite confusing, even for an expert to kind of sort through all this. And this really became a genesis of where we wanted to further take the work, and as we were still working on, and still are working on, the OMEC project, really take it into better analyzing it. So SpectoX is a whole project we've been doing coming out of this that really evolves the FD tool that was developed quickly in 2017. And we have a lot of different goals in this. First and foremost, ideally, on the long run, this is something that gets used, and this has been shown to XC and 3GPP and IETF, so they've seen this tool. Well, actually, maybe not IETF, but XC and 3GPP definitely have. If nothing else, we'd like to provide something where the authors of these documents have some sort of, not closed loop. The people, humans in the standards groups, would never want a piece of software to automatically edit a standard at all. That would create more chaos. But really provide to these editors and authors a document that highlights some of these inconsistencies. So an early output from SpectoX quite literally was a Word document with change marks on it that really highlight the issues that were found in parsing the document. And then that could be then gone through by a human expert, accepted or not, and used to generate improvements in the documents. We also wanted to auto-generate code. We have done that for LTE with YAML specifically, but we wanted to take this to the point where if the specs are easy enough to interpret and clear enough, then we can automate some of the basic process of code generation. Obviously, everybody would love to get through standards more quickly. There are experts, and they still, they might better know where to find a particular item. But for most people that use the standard but don't deal with it every day, just finding where a certain item is highlighted, or documents, multiple documents, can be a pain. So it's always good to have something that helps to make the content searchable. And then on the troubleshooting side, it's actually quite interesting. This is actually in some ways the most valuable for an operator. But there are different roles, obviously, in companies and an operator specifically. And the people that have to keep the network running will often, there's too many words in the standards, and they really want to get down to something that graphically helps them get their job done, especially if it's an outage scenario or something where they need to be moving very quickly and to fix something. So oftentimes they'll get operators, people in the operations team, who will print out a ladder diagram for a particular protocol and paste it up on their cube, or now that we're working from home, on the wall of their house or something. But refer to that, and that's great so long as this it doesn't change. And part of what we're trying to get to is, there have been challenges where someone thought the ladder diagram was the same, and that was last revision. Now it's changed this, and they weren't aware and didn't have the right version. So we really want to get to the point where someone who needs to very quickly get to information they want, and we can tailor this for the operations team, like generating a ladder diagram dynamically on the fly if someone wants to go to a tool and do that. That's part of the goal here. But net, all of this is trying to take the subjectivity out of human interpretation and make this as clear as possible for everyone, not just within our company, but for the industry as a whole. Obviously, there are some things we'll probably enable just within our company. We're not going to help our competitors troubleshoot their networks better. But if we can get the standards to improve the process and get rid of some of these the areas of lack of clarity, overall we all win, and everything becomes more agile and hopefully less buggy as a result. The diagram on the right is pretty complex, but this is what we've talked about as a path forward. 3GPP uses Word today. They actually are going to work on developing their own online tool for writing specifications, and the goal ultimately is to hook SpectoX into that as well. So now here's where we're at, and I think this has been useful for us, and I don't know how far we'll take it. If some of the future stuff we may just make for internal use only, and there's only so much we can fund this on our own, and we're hoping that this also becomes something that other companies embrace, and we can take this out as in an open source manner, or some form that it gets embraced by industry much more broadly than just our company. Like I mentioned, there's over 3,000 stage 3 or the more detailed specifications, defects found. Those have been submitted. Found almost more disconcerting, several dozen stage 2 errors. And the stage 2 logic is so critical that if there's an error there, it propagates and creates more and more issues downstream, no doubt. And so those are really important for us to try to find and help create. We have the YAML code generator, obviously. In 5G, we've done less work on that because it's newer. About 500 issues so far in stage 3. Working with 3GP on PP on new formats to increase the efficiency and how we convey this work. And what we've done for our own standards team, they used to report to me when we're at Sprint. They're now in a different group, but we're trying to make their lives as easy as possible. So they can run the tool, and it will auto-create the Word document with the change request to submit to 3GPP. So they don't have the drudgery of putting all that together, especially when you start talking about thousands of these. The overhead of just doing the paperwork can get pretty large. We're working on more mapping between stage 2 and 3 and getting things broader. It is now being moved to an online version. It initially was a tool that ran locally. And that's something that we're partnering to try to get broader adoption on. And we have some things to do in the future, but like I said, they're not funded. And if they do get funded, it would be probably more for our own internal purposes than necessarily helping the industry as a charity contribution, so to speak. But things like AS1 are super important to the industry, and obviously often tend to be long lead items in getting standards implemented. And so the more we can help on things like that, the better. And I think that's really where we're trying to add some more value, at least internally focused. And then this evolved this summer when we've had some of this work going on with some of our full-time employees, but we were comfortable enough with where we're at with the project after a few years of work that we actually turned and invited interns to come and work on a part of this project. We call it SpectoProcedure. SpectoX, there's a lot of different components to it. X can be any of a different number of formats or outputs. Here we're taking the standard documents and putting them into UML representations so we can try to make them as regular and well formatted as possible. And there's lots of different ways to approach that. And we tasked them to look at different NLP approaches, some of which we had done, some of which we endeavored to do but had not gotten there yet. We had, I should mention this, there's no slide on this, but to try to enforce how, learn first of all, but then help the engineers understand how malformed some of this could be. We did a bit of a manual exercise for a period of a few months. It got to be a lot of complaints on the team, but really taking people and walking through very rigorously, trying to interpret the documents, not in a breezy read, but label them as a, this code would label them as accurately as they could in terms of the specification, where it dovetails and ties into other specifications, and the different key parts of it, what's normative and all that. It was very laborious to do that, but we also learned quite a bit about tagging that helped us when we started to do automated tagging ourselves, and then help direct the interns in the right direction to do the automated tagging as well. Again, the net goal was to try to provide annotations and UML representations that were human readable, but ultimately weren't automatically just accepted as truth, but could be reviewed by a human and accepted, and go from there. Our interns do regularly file patents, and I don't know that there will be any out of this, but there very well may be, because there was some very interesting work done. And there's going to be fewer results shown here than perhaps some of the others, just because of that. One individual in particular took a deep dive on a couple different ways of coming up with this tagging and creating the UML representations. We're planning on using the framework they built and adding to it. He's likely going to come on part-time during the school year just to kind of keep working on it. He's got a lot of interest in it, and we do as well. The approaches here are many, and I would say that part of what we're trying to figure out is how much we really want to take the NLP aspect of this. And we're not going to do any net new invention of a new technique, but I don't know how bleeding edge we want to be versus anything else. So largely we're trying to use libraries where they exist and not do too much novel implementation of our own. But we've definitely found some variances here. I think the highest, as compared with, it's not unclear what the right standard is here, because humans have a hard time being really correct on this as well. But I think we've got about an 85% match rate with the best human results we could come up with as a means of comparison. It's not perfect, and there's room for improvement, but it's a much faster than doing it. It's still actually rather slow itself to digest these large documents in terms of amount of CPU time, but it's still much faster than having people walk through manually to do it. So we're back to the word cloud. I do want to recognize Intel, NGS Labs for all their work and helping us in these programs, specifically the gateway programs. Beyond that, the NLP work has really been more internal and something that it's harder for others to contribute to anyway. They're not as invested in standards as we are, in the 3GPP standards as we are. But it's really afforded us a chance to take this journey. I did forget to mention when I was on the core slide, you see it down there in the word, the 40.4 gigabits per second. That was our record in terms of user plane throughput in one CPU core. So rather than trying to get 10 gigs in one CPU, we ended up getting to the point where we could push 40 gigs through one core. And what limited us, quite frankly, was the NICs we could afford at the time. We didn't have any 100 gig NICs, and we didn't have budget to get 100 gig NICs. But if you look at the number of CPU cores in a modern server processor, and you extrapolate that, even if that's the upper limit, and it most definitely goes above that, but we just haven't bothered to go there. There's plenty of room to do very rich packet processing at a gateway level with all of the sorts of bells and whistles we do as operators, not just merely forwarding in these virtualized environments. And there's we're definitely limited by the I/O and by the number of NICs you could put on a server than anything else. Here's the whole team. A large team of the support group. They were only partially involved. Some of those are standards people that helped with some of the submissions and so on. But the core team on the T-Mobile side, Sprint, and then now T-Mobile side, the Intel group and the GS Labs folks, all worked very hard on this, on the OMEC code for many years, and I think we've got something that's really robust and out there for others to use. And I think everybody on this list should be thanked, and also has done a great service to the industry.